Hello everybody, welcome to this webinar. My name is Mernoush Khabiri. Today I'm going to present antenna design for IoT for Internet of Things with using ANSYS HFSS. If you have any question during the presentation, please feel free to write down your questions in the question box or chat box. I'll try to answer to all of your questions in end of the presentation. So let's start. Just before I start, I'm going a little background about the Ozen Engineering Inc. Ozen is ANSYS channel partner and distributor in Northern California. We sell ANSYS software product and we have training and technical support for that in Northern California. We have consulting services and do simulation projects for our customers. Our office is located in Sunnyvale, California. About ANSYS product, as you know, ANSYS develops engineering simulation softwares and offer multi-physics simulations. They are number one in the finite element analysis, CFD analysis, and also electromagnetic products. ANSYS is CAD independent, and it has the high performance computing capability. Also, ANSYS offers a couple of human body models, like a detailed adult male and female models with over like 300 parts in the material property with the frequency range of 10 Hz to 10 GHz, which are really useful for biomedical applications. Let's see how simulation can help you in your product development. Basically using simulation help you to predict how product design will behave and how manufacturing process will operate in real world environment. So in all time, the process was like the concept, designing, and do the prototype, physical prototype, and testing. So if it didn't work, the engineers should redo all the works and repeat the process. So it costs a lot of time and money. But with simulation, you can look at the total life cycle cost over time, and you can go through thousands of iterations before committing to any physical prototype. Here are ANSYS Technologies. ANSYS supports have product in electromagnetic product, both in high frequency and low frequency. In high frequency products are HFSS, SI-Wave, Q30 extractor, and designer, and in low frequency, especially for electromechanical application, it's Maxwell and Simpler. Also in structural mechanics, they support from linear static to high speed impact, and in fluid mechanics, they support from single phase flows to multi-phase combustion, and also system simulation from data sharing to multi-domain system analysis. But today I'm just going to talk about the ANSYS HFSS, which is a software in high frequency electromagnetic. One of the ANSYS capability is multi-physics simulation. So if you are using the electromagnetic product, for example, if you are using HFSS for electromagnetic and 3D electromagnetic modeling, HFSS is integrated in the workbench for coupling electromagnetic effect into multi-physics analysis. So basically you can couple the HFSS through the workbench to the ANSYS mechanical for thermal analysis or structural analysis. So you can do the analysis for temperature and deformation as well. So this integration allows engineer for easy data transfer and simulation management. Our topic today is focused on using HFSS for antenna designing and for IoT applications. So let's see what exactly is IoT. The IoT, or the Internet of Things, is a network of smart products, or let's say things, that use embedded sensors, software, and electronic components to communicate with each other over a network. So the communication data can be analyzed by cloud-based software to drive actionable information. So basically it's include things or a smart product, gateway or network or communication lines, and also cloud for data processing. So where ANSYS can help you in IoT application, ANSYS can help you to design your smart products. So, and when engineers are working on IoT design, they should consider some challenges like small sizes, low power, or sensors, and they should check for connectivity, safety, reliability, platform integration, and durability. So these are the applications that ANSYS can help you to design your smart product, like chip package system design, antenna design and placement, sensor and MEMS, power management, embedded software development, designing for harsh environment, and virtual prototyping. So, but today our focus is in antenna design and placement or integration in a platform. We want to see how ANSYS HFSS can help us with that application. So when you talk about the IoT, it means antenna everywhere, because all of those devices need to communicate wirelessly. You need wireless communication, so you need antenna everywhere. And the other channel, first challenge would be designing the antenna. After that, it's integration of the antenna in a complex platform like an aircraft or a car or a smart wearable. So these are the challenges for like large electrically structures, so that you need to do simulation for them. ANSYS HFSS is a 3D full-wave electromagnetic solver. This solver is based on the finite element method, and it solved the full-wave equation for Maxwell equation based on finite element method, and you can extract S parameter, impedance parameters, or you can have the result for near field, far field, or electromagnetic distribution or current distribution on your device. One of the advantage of the HFSS is automatic and adaptive mesh, so it makes the engineer's life easier, so you don't need to be worried about the mesh refinement and the convergence of your design. So here is a big picture of the HFSS solvers and features. Basically, HFSS is based on finite element method, but it has the integrated equation option HFSS-IE, which is for open radiating and scattering problems, and also it has HFSS transient, which is ideal for fields that change versus time and space, like scattering locations, and HFSS SBR, which is shooting and bouncing ray, and it's the former Savant. So it's a new feature added to HFSS, which is it's good, really good for the electrically large structures, especially for the platform when you install the antenna in a large platform or complex platforms. And RF radio frequency and SI signal integrity options is included there. So for example, EMIT is one of the new features that you can use this solver for the EMI, electromagnetic interference, and look at the RF co-interferences. So it has A-Link. It means that you can import any ECAD or MCAD file from other softwares to the HFSS. And also it has the high performance computing option, and also optimetric option to doing the parametric analysis or optimization or tuning, and also distributed solver option. So HFSS is integrated in ANSYS electronic desktop, where you can find all of the ANSYS product, electromagnetic product, like HFSS, circuit design, HFSS-SBR, HFSS-IE, or even low frequency product like Maxwell or simpler, all included in ANSYS electronic desktop. HFSS, as you can see here, has the 3D modeling. It has 3D layout modeling for board or traces analysis, and also it has integrated circuit design that you can use it for example, for antenna modeling. You can use it for the matching network analysis or a system analysis. Let's look at the HFSS workflow. So basically, start with the geometry. You can create the geometry from scratch in HFSS GUI, or you can import it from any ECAD or MCAD file that you have, or you can use SpaceClaim or ANSYS SpaceClaim and ANSYS Design Modeler to create the geometry and link it to the HFSS. After that, you need to define the material. HFSS has a complex, a lot of the material library is really good, and even if the material you are interested is not there, you can add your materials there. And then you need to assign the boundary condition and also the excitation, and in the end, after setting up all of these options, then you can solve the problem. So when it's a start to solving processes, it's starting with the initial mesh. So it's solved for that, and you can use the high performance computing HPC option to make it faster and save time. So, and then if it's going to the adaptive meshing, and after it converges, it goes to the frequency sweep, and again in frequency sweep you can use HPC, and in the end it's the post processing, so to see the results that you are interested. So in the geometry part, as I mentioned, you can bring any geometry from Cadence, Zuken, or from SolidWorks, or in ANSYS Workbench, you can use ANSYS SpaceClaim or ANSYS Design Modeler to import the geometry to HFSS, or you can just create your model in HFSS GUI from scratch. So automatic and adaptive meshing. So basically HFSS start with the initial mesh and doing the mesh refinement. So it iteratively adds mesh elements in area that needed more mesh. Like for example, this antenna design, you can see it's increasing, it makes finer mesh around the metal parts. So it continues the mesh refinement till achieve the goal, and then it's gonna stop and goes to the frequency sweep. But if it's not satisfying the goal, it's going back and do the mesh refinement, so till get the proper response, as you can see here. One of the other HFSS feature is you can use it for array antennas. So you can use a unit cell array analysis. Basically, it's like a infinite array antennas, but also for finite array, you have an option of explicit, which means that you should put all the antenna model, all the elements in the simulation. So for sure, this one gonna takes time and a lot of RAM to run the simulation, but there is another option that helps you. It's the finite array domain decomposition method, finite array DDM. This is This is the option that it's not using all the array all the elements. Basically, it's copying the mesh and everything in other element places. So this kind of simulation reduce solve time and also needs less RAM to run. So the results from DDM and explicit are in good agreement. So it somehow saves time and memory for you to run the simulation. And HFSS optimetric option. So in this option, HFSS has like you can do the analysis for parametric optimization, sensitivity, statistical, and tuning. So let's say, for example, you design your antenna and it worked perfect, but when you place it in a platform, the antenna performance is going to change. So you need to do like a parametric analysis on the like radiating parameters or the parameters that are important. Do the parametric analysis to improve the antenna performance. Also, you have an option of real-time tuning. So, for example, if you have your S11 S parameter, you can use the real-time tuning based on some parameters like feed point or patch length or whatever is your design or parameters are in your antenna, and see basically quickly explore effect of small changes on your S parameter. This is a really useful feature for in HFSS for designing the antenna. If you need a quick start in antenna simulation, HFSS has an antenna design kit. This antenna design kit is a standalone GUI-based it's a standalone GUI-based utility which automates the geometry creation, solution setup, and post-processing report for common antenna types. So these are the antennas that are included in this antenna design kit. Basically, the common antennas like dipole, patch antenna, spiral, Vivaldi, and PIFA antennas. So if you are not familiar that much with antenna design, this kit can help you a lot, because it's basically you just need to select the desired antenna from the list here and specify your frequency or specify your parameter and say create the model. So, and it's going to create the model in HFSS, and you're going to have the whole antenna simulation with the solver and all the solved and with all the results. So it's going to help you to start with antenna design. It helps a lot. So the other, so we talked a little about these solvers in HFSS. Basically, if so you can use the HFSS 3D finite element method, HFSS 3D electromagnetic solver. If you have a electrically large problem, you need to use the SBR or method of HFSS IE. For like a complex platforms and large platform. So these are the solvers that we talked about. I'm just briefly going through the HFSS-SBR because this is a new solver in HFSS. It's a former Savant that it's a Dell Keras company that is acquired by ANSYS. So this is a shooting bouncing ray. It helps a lot for the electrically large platform. For example, if you design the antenna in HFSS, you can bring it in the HFSS-SBR, so place it on your platform, whatever is your platform, and it's using the shooting and bouncing ray technique to solve it. So it's going to save you a lot of time and for sure the computation resources that you need, it's going to save you a lot. So it's pretty much faster than even HFSS IE. The other option, which is EMIT, it's again from the Dell Cross company. So it's for electromagnetic interference analysis. So it can predict and prevent like interference in your whole system simulation. So if you have a platform, you have multiple antennas, and you have radiations, different radiation, you can look at the interfaces, and it tell you, like for example in red spot, that you have interfaces, so, and it help, and you can put a filter or do something or change the placement of antenna to basically eliminate the interferences. I'm going to through some of the antenna applications, like but basically for antenna design you may want to install it on a large or complex platform, or you can have them on mobile devices, or even for biomedical application. A lot of implantable medical devices now have antennas, so you can use the antenna for phase array use HFSS for phase array antenna design. I'm going through some couple of examples and show you the process in HFSS, and also I show the one of the examples in the software, in HFSS software, as a demo. The first thing, the antenna I'm going to type is antenna for medical application. This is a PIFA antenna. This antenna, as you can see here, is designed in HFSS in free space for medical implant communication service, MICS band, 402 to 405 megahertz. So just a background, the wireless telemetric link are needed to transmit the diagnostic and therapy and vital information to the outside of human body. So this antenna is supposed to integrated in a medical device, which is an implantable device. So first we designed the antenna in a Fourier space. As you can see, it has a sharp and deep S11 response, and this kind of antenna doesn't need like a high bandwidth. So the response is good, and also you can look at the impedance. It's in 402 megahertz. It's almost matched. But then the process was to put the antenna in the human body model. As I mentioned, ANSYS has a human body model that has like over 300 parts, like organs, muscles, and they are all there, and they are all frequency dependent for electromagnetic analysis. So as you can see, when the antenna located in the human body is a lossy media, so the antenna performance gonna change. And so we did a parametric analysis for antenna for the radiating part, like the strip of the some part of the PIFA antenna. So we did a parametric analysis to get the to improve the antenna performance when it's implanted in the human body. So you can see these are the kind of results that we can extract, like look at the 3D radiation pattern of the implanted antenna inside the human body, or we can look at the 2D radiation pattern of the antenna. So you know, the wide and fast-growing application of wireless devices yield to a lot of concerns about their safety standard related to the electromagnetic radiation effect on the human body. So, for example, if you have a device that you want to bring it to the market, you have to satisfy the FCC regulation for SAR value. SAR is a specific absorption rate. It means that the the amount of power that is absorbed by human body tissue from a device. So basically, if you want to bring your product to the market, you need to satisfy FCC regulation or European standard for the SAR limit. So doing this HFSS simulation help you with that, because HFSS has an option for SAR measurement. So as you can see here, the device is located in the human body chest. So as a the local SAR, we can plot the local SAR value distribution on the human body, and you see just the most absorbed power is around the chest and not around the all other body parts. And also here is again for the internal organs, SAR measurement for internal organs. So these values are all lower than the FCC standard. So basically this kind of simulation give you a rough idea of the SAR level of your device before physical prototype and test it in the lab. So here I'm going to the HFSS file to show you. Here is the model that I talked about. This is the human body, as you can see here. This is the human body with all the details, all the organs are included here, and all of them are like frequency dependent material. So in HFSS, as you can see here, or in ANSYS electronic desktop, the project is open is HFSS, but you have all other options here like 3D layout, HFSS IE, or when you have the Savant, HFSS-SBR or EMIT, and also low frequency product, and also circuit design options. But the project here is the human body with the antenna integrated in the body. So as I mentioned, first you need the geometry. Basically, I imported this geometry. It was created before, so I just created the antenna model here. So you always need to define the boundary condition, especially when you have a radiating boundary condition. You need to define the boundary condition around the human body model. Like I have a radiation box here around the body, and there are some rules to how what would be the distance of radiation box from the radiating part, which is antenna here. So we can use PML or radiation, but the recommended one is that always the radiation box should be more than lambda over 4 for the from the radiation object or radiating product or structure in your design. So this is the whole model that you can see, an antenna is integrated here. So the result that you can see here, we had the, as you can see, we had some parametric analysis here to find to improve the antenna performance, because after we integrated the antenna in human body, we had a shift in the resonance frequency, and the value of S parameter wasn't good enough. So we did a parametric analysis to get the proper result, and also you can see the result for the impedance, real part and imaginary part, and in the end I think it was the we could improve the antenna performance like that, and it's almost matched. It's not the exact value. I mean, it's not like real part 50 ohm or imaginary part 0, but we can fix it with some tuning and also some impedance matching. It can be fixed. Also, you can bring all of these in the post-processing in the results. So the other things that you can plot like radiation pattern, 2D radiation pattern or 3D radiation pattern of antenna as well. The other thing that Let me close those ones. Also, you can look at the field distribution around the human body, like a level of the electromagnetic electric field around the human body, like defining some virtual surfaces to look at the field distribution. And also you can plot the SARF value. So here you can see the SAR level. So for the whole human body model, you can see that it's not high. So basically, it's this device doesn't have any problem with like FCC or European regulations. And also, for example, you can plot SAR on a specific part of human body. For example, if brain is important for you, let me just bring the brain. So you can see the amount of absorbed power or specific absorption rate, SAR value in the human brain. So these are that kind of analysis that you can do. And also, you always can check your antenna parameters here, like all the peak directivity, peak gain, and all the values here. So let's get back to the presentation. The next example of antenna I'm going to read is antenna for smart wearables. Doing the design for a smart wearable is a multi-physics design. It involves a lot of process like electronic parts, also system design, mechanical part like user experience, heating experience, manufacturability, and all the analysis like that. You need the embedded software to get the final product. But right now I'm just going to focus on antenna performance and antenna design using HFSS for this application. So here we have this device, this wearable watch, and this voice, so a smart voice supposed to have a Bluetooth antenna operating in 2.4 and also a biosensor antenna operating in 400 to 450 megahertz. So the first step would be designing the antenna on a PCB in free space. So you can design this antenna in HFSS 3D easily and look at the antenna performance. You can see the S11 or return loss or 3D radiation pattern of antenna or 2D radiation pattern of antenna, so you can get the antenna performance result. But next step would be wrapping the antenna around the wrist. So for wrapping, you can use the space claim geometry creator, so to wrap the antenna on your structure or your model. So, and with wrapping the antenna performance gonna change, and you're gonna have some shift in resonance frequency. So we need to do some parametric analysis and some optimization to improve the antenna design, both for the biosensor antenna and also for the Bluetooth antenna. As you can see here, with doing the parametric and optimization, we could bring back the antenna, improve the antenna performance, and bring back the resonance frequency to the pointed frequency. Here, also in HFSS, you can do the full system simulation. Like if you have different systems, like I mentioned, like you have different antennas or different noisy, different devices that has radiation, you can do full system simulation in HFSS. So to look at the like electromagnetic field distribution, look at all the radiation pattern of the antennas that are involved, and for example, you can use it for the SAR measurement to see how would be the absorbed power by the human body around the human body. These are the kind of analysis that you can do, and it could be like a virtual prototyping before you get your device to the lab for measurement. Uh, the other example is antenna beamforming at 60 gigahertz. Most of the time, basically the step for design is designing the antenna in Fourier space, then integrate it in your device, like a cell phone or in a router, and then you are placing it like in a workplace or in a room or a office. So you want to look at the whole you want to look at the whole area and see the interference and interaction of the fields. So uh, for this case, you need basically multiple solver to do this simulation. Basically, no single solver technology can address this multi-scale problem. So here even ANSYS offers multiple solvers working together to model this whole system, because this is the basically when you install the antenna on a platform here, it's going to be a multi-scale problem. So you have very large structures compared to the wavelength. So basically electrically large structures. So for this case, for example, the first step would be designing the antenna for the mobile device, and then designing the antenna for the router, and then look at the full system simulation. So first step, you can design the antenna in HFSS like in a Fourier space, and then do the full array analysis and array design, and then integration of the antenna in your platform, which here is mobile devices. So these are the results from the single antenna, which is designed for the cell phone. And also here you can see the performance of antenna for an array antenna integrated in the cell phone. The next step is the same for the router. You need to design the single antenna and the array ones, and you can see here you have multiple arrays. So for all this simulation, we're using HFSS for designing just the arrays, HFSS-IE for like multiple arrays, and for surfaces in open environments. And in the end, we're using HFSS-SBR, which is shooting and bouncing ray option for the whole room simulation. These are the performance radiation pattern of antenna for the router, as you can see here. Okay, now we're gonna do the full simulation here. As you can see, the whole area and the whole room is really large compared to the wavelength. If you want to do such a simulation in HFSS based on finite element method, it's going to take forever, and it needs a lot of computation resources. But with shooting and bouncing ray, it's going to save you a lot of time and computing resources as well. So the way it's working is that basically it's doing the beamform training. It's scanning the all the arrays. Basically it cycles through the sectors to find the optimal pattern or optimal path. So basically, as you can see here, it's the mobile devices is this way. It's scanning the array, and also the same for the rotor. And when it's doing the shooting and bouncing, it's going to find the best path, as you can see here, for the communicate. So basically, it's using the beamform training helps to optimize beam pattern sectors. So the router has multiple arrays that can each be scanned to support a large number of connections. And during the beamform training, optimal arrays selected, and and beam refinement can be done to find the optimal path for the connection. So this way, with these arrays, basically router can support a lot of connections. So as you see here, it was a use of like different solver of HFSS, HFSS 3D, HFSS IE, and also HFSS-SBR for do the whole simulation. I think that was my last example. Yes, so I'm done with the presentation. Thanks for your attention. So I'm going to check the question box or chat box if anybody had any questions. So if you have any question, you can write it down in chat box or question box and I can answer it. Or you can send me an email. You can send the email in info@ozeninc.com and ask your questions. If you have any question, we will be happy to help you and answer your questions. Let me check again. So apparently there is no question. So thanks for attending. Have a good day.